All right, we're going to finish out with a little multiple choice, a couple multiple choice problems. This first one gives us the graph of f prime of x, the derivative, but it asks about f of x. It says how many relative maxima does f of x have? People that don't read the directions think, how many maxes? This is the dumbest question I've ever seen. 1, 2, 3, 4, 5. Well, no question is going to be that simple, and that's because that's not the right answer. Okay, so you just got tricked. You need to slow down. You need to read directions. Now let's get the problem correct. What I know about derivatives is this. If f prime is positive, meaning I'm above the x-axis, let me color that portion of the graph green. All of this part of the graph, the derivative is positive. So the original graph, it's not shown, but if it was, it would be rising during that period of time, and it would be falling where you see all this blue, because the derivative is negative there. Okay, if you want a relative max, you want the derivative to have gone from positive to negative. Or in this case, in our picture, you want the graph to go from green to blue. How many times do we go from green to blue? Well, it happens once here. It happens again here. And that's it. And so the correct answer is choice B. Twice. 2 maxes. Here's another multiple choice. It says the graphs of f of x, g of x, and h of x are shown below. Oops, you know what? I forgot the prime signs. Let me fix my own error here. Because clearly you can see that it's f prime, g prime, and h prime. And that is a big deal. So the derivatives are graphed. Again, I'm going to color my drawing before I talk to you guys. On all of these pictures, anything that's above the x-axis, I'm going to turn green. And anything below, I'm going to color red. This coloring is a nice diversion from having to think just for a moment. I kind of like it. Reminds me of my younger years, like first grade. Back when life was simple. All right, great. So as you can see, the green areas would be where the original graph, not pictured, is rising, and the red regions would be where the original graphs, again, not pictured, are falling. Well, the first thing that strikes me is that h of x would have to rise all the time because its derivative stays positive between a and b. And if you're rising all the time, you're not going to have a relative minimum. So h is out, which means it can't be choice C. It also can't be choice E. So I'm down to either A, B, or D. So let's investigate. We'll start with what a relative min would be. A relative minimum means that I was falling and now I'm rising. And again, don't look at these pictures with the red and green. Think about if the original graph is falling, it means its derivative had to be negative. Its slope had to be negative. So you want to go from red to green. And that happens here. And it also happens here. So both f of x and g of x do have relative minimum values between a and b. And so the correct answer is choice D.
Number 15 is also patterned after a common style of FRQ.
It says a function f of x is continuous on the closed interval 0 to 4, and you've got some selected values in the table. Find the x-coordinates of all local extrema of f of x on 0 to 4. Notice they're cutting us a break because the 0 and the 4 in their directions are curled, even though they're not up here. Since they're curled down here, I don't have to consider endpoints. That's awesome. So I just have to find the maxes and the mins that are in the middle. Well, again, you know that a max is going to occur when the slope or derivative was positive and then suddenly turns negative. Okay, here's the derivative right here, f prime. Is there any place where the slope was positive and turns negative? And the answer is yeah, right here. You went from positive to negative at x equals 3. Now I need to write that as a complete sentence because they explicitly say explain your reasoning. Okay, we're also looking for a relative minimum, and that would be found when the derivative changes signs from negative to positive. And that also occurs, it occurs right here from negative to positive. The College Board stuck a DNE in the middle to see if they could get people to not answer the second part. That causes some people to shy away. But you think about it, a derivative doesn't have to exist for there to still be a minimum. What if you had a cusp? Ouch, right there. A cusp can be a minimum, and here you had the first derivative negative, you were falling, then you were rising. The derivative right here at this point didn't exist, but it's still changing from negative to positive. So we're okay. There is a relative minimum at x equals 2. So we have to state that in a similar fashion. And that's what we're looking for full credit. All right, at number 16, we're going to go back and revisit problems that we did the other day, finding the absolute and relative extremes. Again, we have a closed interval from -8 to 10, so we have to watch the endpoints. The reason this one is different is because the pattern is going to get broken. Remember, we had like rising, falling, back and forth, and a lot of people were like, why do we have to try all these regions? Isn't the pattern just going to stay, the same? And I said, oh, there are exceptions. I'll show you some, and this is the first of several. So here it is. I'll just take you through step by step. Obviously, if you want to find maxes and mins, extreme values, you have to take a derivative. Before you waste your time doing the quotient rule, try factoring first. Factoring is your friend. Trust me, folks. If you factor, it'll look like this. The x plus 2's are going to cancel out. That'll just give you 1/2 x. And if you take the 1/2 x and distribute it, you're going to get 1/2 x squared minus 3x. So that original problem got majorly rewritten before we ever started. And now taking the derivative doesn't require a quotient rule at all. It's super easy. You can probably do it in your head. And the derivative comes out to be x minus 3. And obviously setting x minus 3 equal to 0 gives you 3. Sorry, the answers are visible already. Oh well. Nothing I can do about that. Let's move up a bit. Here's what happened. There was a discontinuity at x equals -2. Remember that you can't really divide by 0, so we have to honor that. So our critical number was 3. I'll throw the -2 in there as well. Just get rid of this thing entirely. And then what happens is if you try something between -8 and -2 into the derivative, let's say that you tried, -5. And here's the derivative. Clearly you can see that -5 makes it negative, so yeah, it falls. If you try something between -2 and 3, let's say you try, a 0 or a 1, it's still going to fall. So it's falling, then rising. So the pattern doesn't alternate. You have to be careful. Now again, if you look at the endpoints are allowed to be maxes and mins. So it's basically falling and then rising when you get to the right. So the possible absolute maxes would be at -8 and at 10. And so you look at those two numbers. 56 beats the 20 out. So -8, 56 becomes the absolute maximum. The 1020 can't be a local max. It's an endpoint. It's just not considered. It's out. And since this thing doesn't bend anywhere else, the minimum that happens at x equals 3 is an absolute min. And that's the point 3 comma -4.5. Okay, 3 problems remain in this section, and this is an important skill to have. You're given f of x, you have to sketch a graph of the derivative. And if you look at the slope of this orange graph, on the left-hand side, the slope is just -1 for quite some time. So that means that the derivative, if I was to graph it, would be -1 until I get to right here. I'm going to have an open circle. Let me label this. This is f prime of x. I'll make it green. Then the derivative sort of changes. As you can see, right here, the derivative is, or the slope is probably right about 2 or so. By the time I get to right about here, looks like the slope is only right about 1. By the time I get here, the slope is maybe 1/4 or so, or 1/8. In fact, the slope is heading towards 0. So it's going to do this and come in like an asymptote. And you can't really see it because you've got a bit of a corner cuspy type thing. But if you were to zoom in right here, you would see this. And the slope in this part would be so steep and yet positive that you're going to be going up to like 4, 5, 6, 10, 100, infinity. And so it's going to look like that. Let me get rid of the rest of the distracting stuff and we'll see our final answer. Then I'll talk to you guys some more. Okay, what you see now is the final answer. The derivative graph does have discontinuity. There's infinite discontinuity at x equals -2 on it. And the reason why there's discontinuity is the original graph has a cusp. And that's one of the 4 things that ruins derivatives. So there's no derivative along that same vertical line. Remember, you can't have cusps, corners, vertical tangents, or discontinuity in your original orange graph. Okay, let's try another. The original graph, f of x, is in purple. Sketch the graph of the derivative. This time I'll make it blue. As a teacher, the most important places to look for are right here and right here. So if you're doing this on a quiz, I'm finding the max and the min of the original purple graph, and I'm saying, does the student realize that the slope is 0 there? And if you realize that the slope is 0 there, you better come down and your graph of the derivative better be at 0 on the x-axis. Same thing here, you better come up. You better have a dot right there. If those 2 dots are not there, your graph's in trouble. Your answer's in trouble. Okay, let's look at some other places. Right about here, to me, that looks like a slope of, I'm going to say -2. So I would go to, -2 right about that location. Over here, to me, that looks like a slope of more like +2, maybe even +3. Here, again, same thing. That's a slope of +3, +4, maybe even +5. All right. Again, you can see that I'm kind of guessing, but it says sketch a graph. So this does not have to be perfect art. It just has to be believable. Okay, I connected my dots with a curve, and that is the derivative. You know what? I feel good about my answer, too, because the purple graph, the original, was a cubic, or third power. We know that we take a derivative, we go down by a power, so it makes sense that I should be looking for something that would be squared, and I have what looks to be a parabola. Now, again, the level of accuracy should be good, but it doesn't have to be great. Again, it's a sketch. The way College Board's going to do this is they're going to give you the purple graph, and then they're going to say, in a multiple choice format, which of the following graphs could be a picture of the derivative? And they'll put the correct answer in choice C. They'll make something that looks like my answer. And then the other answers will just be totally stupid. They'll be straight lines, or they'll be whacked out curves, and maybe a parabola going the wrong way. And you should be able to spot the answer. You're like, all right, it's C. So again, this does not have to be a Pablo Picasso type work here. All right, last problem. Here we go. We have to sketch one final curve, and it says a smooth curve, so we're not going to have corners or cusps in it. It doesn't say continuous, but smooth kind of implies that, so I think I'm going to make mine continuous. It does have to go through a couple points. Let me put those on the graph now. It has to go through -1, 3. It also has to hit the point 4, comma, -5. Okay. And then we have some properties. It says this. The derivative is greater than 0. If the first derivative is greater than 0, that really translates to the original graph, which is what I'm trying to draw, is increasing. So this graph is increasing if I'm less than -1. Let me go ahead and put a little dotted line in here. That dotted line is not meant to represent an asymptote. It's just training wheels for me. If I'm to the left of that black dotted line, my graph has to be increasing. Okay. And then it goes on to say that the first derivative is negative. In other words, the original graph falls if I'm between -1 and 4. So it's going to fall the rest of the way. Oh, but you know it's going to rise again. I didn't see this the first time. The derivative is also positive once you cross this next dotted line here at x equals 4. You're going to rise again. So really, they're having me graph an S-curve, and the only two things that have to be on my S-curve, it should look smooth. Mine's debatable, but the point -1,3 has to be a local max, and the 0.4, -5 has to be a local min. And that does it for section 3.3. That was a big section, a lot of information in there, but hopefully it made sense. And I'll see you on the next lesson. Take care.